Hey everyone, today we're going to be talking about continuity as we discussed in the previous video, and we're going to go over some examples. We're going to go over a bunch of different questions, a bunch of different problems, and we're going to use the concept that we used in the study of the previous video to solve these questions, right? And then we're going to go over horizontal asymptotes and solve a bunch of different problems as well. Right, so let's get right into it. I have this function g of x, which is x minus 1 over 3x plus 6, and I want to prove that this function is continuous in this interval, negative infinity, negative 2. Right? How do I proceed? I say let a lie in this interval between negative infinity and negative 2. What I do is that I say limit x into a, x minus 1 over 3x plus 6. Solve this using limit laws. I split it in the numerator and denominator. Split it further, I get limit x into a for x, then 1, and then 3x because I can take the 3 outside because it's a scalar, right? And then finally 6. And then when I find the limit after all this stuff, I have a minus 1 over 3a plus 6, which is what I would get if I just plug in a for this function right here. And that's what you want to prove, right? If you remember from the previous video, you want to show that LHL is equal to RHL is equal to f of a, right? Where a is the value that x is trying to approach, right? Or you want to prove, if you combine LHL and RHL, limit x into a, f of x is equal to f of a. And that's what we did here. We said that a lies in this interval because that's the interval that we're concerned about. And we say that limit x into a, for f of x, here we have the function g of x instead, is equal to g of a, right? And that's what we proved. Right, that's the first question. Let's look into another problem now. Alright, let's say I have this function f of x is equal to x squared minus x minus 2 over x minus 2. And you want to make this function continuous everywhere. We know that this function is discontinuous at x is equal to 2, right? Because when I have f of 2, that is going to be 0 over 0, and that's indeterminate. However, our task is to make this function continuous everywhere. How do we proceed? We say limit x tending to 2 of f of x, which is x squared minus x minus 2 over x minus 2, right? How do I can factor the numerator into x squared minus 2x plus x minus 2 over x minus 2, right? And then I can factor it further by writing it as x minus 2, simple factorization going on here. And then finally this x plus 1 times x minus 2 over x minus 2. I cancel the numerator and denominator because I can. Now I'm left with x plus 1. I plug into here and I get 3, right? So the limit for this function when x is approaching 2 is 3. So finally, how do I write this function? I can write this function as this, as a piecewise function, where I write the same thing, x squared minus x minus 2, and then 3. And x squared minus x minus 2 is the value this function takes when x does not equal to 2. And 3 is this value is the value this function takes when x is equal to 2. Why do we do this? It's pretty straightforward actually. We want to prove that f of 2, because 2 is the only part of discontinuity for this function, right? F of 2 should be equal to limit x tending to 2 of f of x, right? That's like the condition that we discussed before. However, we were not able to do that before because f of 2 was initially 0 over 0, indeterminate. But now if I write this function as, when x is equal to 2, this is the value this function takes. When I find the limit for x tending to 2, that is obviously going to give me 3, as I just proved. So this is how you can make a discontinuous function into a continuous one. Alright, let's look at another example now. And in this question, you're asked, say, to find the point of discontinuity. So I have the function 1 over 1 plus e to the 1 over x, right? This is the denominator, that's the numerator 1, right? And if you're asked to find the point of discontinuity for this function, two things should pop into your head. First one, when my overall function, the denominator is 0. However, we all know that the exponential function, that is not going to give me negative values or 0, right? Because the only way my denominator is going to be 0 is if e to the 1 over x is negative 1, but that's not possible, so we rule that option out. What is the other point of concern? Point of discontinuity, probable discontinuity. It's that I have 1 over x here. I have x in the denominator. even if it's like, to the power of e, it's still in the denominator. So when x is gonna, assume the value of 0, that's gonna be a point of concern for us. So we investigate that further. What do? I write the left-hand limit x tending to 0 minus of this function 1 over 1 plus e to the 1 over x. I can write this in terms of h, which gives me 1 over 1 plus e to the 1 over 0 minus h, which is simply h tending to 0, 1 over 1 plus, so I have 0 minus h, that's going to be negative h, and I can write this in this way, right? So what I did is that I have 1 over minus h here, right, 0 minus h, which is minus h, and since I have a negative in my exponent, I can take the reciprocal of it. So this is how I write this, right? Now, let's see what happens when h is tending to 0. When h is going to go to 0, right, e to the 1 over h is going to be e to the 1 over 0, which is e to the infinity. 1 over 0 is, limits tell us that that's infinity, right? So e to the infinity, that's what I have here. This is infinity now, right? Because e to the infinity is infinity. So I have this value being infinity. What would this value be, right? This part. That's going to be 1 over infinity, which is 0, because I'm dividing 1 by a really large number. So then that's going to be 0. What am I going to be left with? 1 over 1 plus 0, which is just 1. So this is my left-hand limit for when x is approaching 0, right? Now let's try to find the right-hand limit. I have 0 plus 1 over x, and instead of 0 minus h, I'm going to switch this to 0 plus h. Alright, and then I write this further as limit h tending to 0, 1 over 1 plus e to the 1 over h. Initially, in the previous, when I was trying to find the left-hand limit, I had 1 over 1 over e to the 1 over h, right, for this term, because I had a negative in the exponent. But now it's just this. Let's see what happens now. When h is going to go to 0, this is going to go to e to the 1 over 0, like in the previous thing. But after that, it's going to be e to the infinity. This term now, is going to go to infinity. Which means that my overall denominator is going to be 1 plus infinity. That's just infinity, right? So this whole thing is going to go to infinity. So what am I going to be left with? 1 over this infinite value, which is going to give me 0, right? So now I know that my left-hand limit is 1, and my right-hand limit is 0, which means that there's a point of discontinuity when x is tending to 0. So that's how you look at this question. And this was a little algebraically difficult problem. It's difficult to, it's easy to mess up with these things when you have like exponents and stuff, but the strategy that I would recommend is, find the reciprocal, try to break the problem down. Alright, so now we're going to go into one of my favorite questions. I have this f of x, which is a piecewise function. I have x squared minus 4 over x minus 2. And this is the value this function takes when x is less than or equal to 2. Then I have ax squared minus bx plus 3 when this is the, when x is less than 2. And then finally 2x minus a plus b, which is the value this function takes when x is greater than or equal to 3. So I have this is a piecewise function, right? X squared minus 4 over x minus 2 when x is less than 2. When the x lies between 2 and 3, I have ax squared minus bx plus 3. And when x is greater than 3, this is the value this function takes, 2x minus a plus b. How do I solve this question? If I'm asked to find the values of a and b, what do I do? Well, you're given that this function is continuous everywhere, which means that it's going to be continuous at x tending to 2 and x tending to 3. Let's see what we get. So let's find the left-hand limit for x tending to 2, right? How do I write this out? Simple. Limit x tending to 2 minus x squared minus 4 over x minus 2. Because when x is less than 2, that's the left-hand limit, right? So I'm just going to leave, I'm not going to use h here, just for simplicity purposes. So I can write x squared minus 4 as x minus 2 times x plus 2. And I can cancel the numerator and denominator out. And I'm going to be left with x plus 2. And when x is approaching to the left-hand side, you're going to get 2 plus 2, which is 4. So that's my left-hand limit when x is approaching 2. Let's find the right-hand limit for when x is approaching 2, right? But now I consider this middle function, right? So I have limit x tending to 2 plus ax squared minus bx plus 3, right? So what I can do is that, this is a straightforward quadratic equation function that I have, right? So I can just plug in 2 here. What would that yield me? That would give me 4a minus 2b plus 3. So the left-hand limit gives me 4, and the right-hand limit gives me 4a minus 2b plus 3. I can just plug in the value here, right? I don't have to worry about the denominator in this case. Here, I had to cancel out the terms in the numerator and denominator because I was just going to get 0 over 0 because that's in an indeterminate form. So that's why we get a 4, right? That's how we proceed. But here, there's no such problem. I can simply plug in 2 here, and this is what I get. So now, I have these two values, and I can use them, right? What I can say is that since this function is continuous everywhere, which means it's continuous at x is equal to 2, I can say the left-hand limit and the right-hand limit are the same, which means that 4 is equal to 4a minus 2b plus 3, right? So this is my first equation. Now we proceed in a similar fashion with x tending to 3. So let's find the left-hand limit for when x is approaching 3. I have limit x tending to 3 minus, I'm going to go with this a little quicker. So ax squared minus bx plus 3. I can just plug in 3 again. I get 9a minus 3b plus 3. Let's find the right-hand limit now when x is approaching 3. So obviously when x is greater than 2 and less than 3, this is the left-hand limit. This is the middle. The middle function is what I'm going to consider when x is approaching 3 from the left side. For the right-hand side, this is the last function that I'm going to use. So I have limit x tending to 3 plus, right, the right-hand limit, 2x minus a plus b. Plug it in 3 simply, I get 6 minus a plus b. And by the same logic, I know that this function is continuous at x is equal to 3, right? Which means the left-hand limit and the right-hand limit have to be the same. So what I can write this as is this, right? I know 9a minus 3b plus 3 is equal to 6a minus a plus b. I can write this as, I can take the a to that side, I get 10a. B to that side, minus 3b minus b is going to give me 4b. And then, I have 6 on this side. I send 3 on the other side, so that becomes negative 3 now. And that's 3. So this is the other equation that I have. Now, I have 2 equations and 2 variables, right? A and b. So I can use both these. So I can simplify this further to say 4a minus 2b is equal to sending 3 to the other side is equal to 1. And the other equation is 10a minus 4b is equal to 3. I solve these out. I'm not going to solve this right now, but after you're done solving, these are the values that you're going to get. A is equal to 1/2 and b is equal to 1/2. So the fact that the fact that was given to me was just this, that this function is continuous everywhere. I can use that fact to say that this function is going to be continuous at 2 and 3. So I found the left-hand limit for 2, the right-hand limit for 2, and I found an equation for that. I found the left-hand limit for x tending to 3, and then the right-hand limit for x tending to 3. And I know that let addition and R shall add x is equal to 3 is going to be the same, right? So I get another equation after that. I use these 2 equations to find the value of a and b. So this is how you solve this question. Right, let's look at another problem now. I'm not going to go too much detail for this one. It's just a provisional concept. So I have f of x is equal to 1 over x. And g of x as 1 over x squared. If I'm asked what's f of g of x, right, the composite function, I just plug in the value of g of x for x, right? So I have 1 over x squared, which is just x squared. Straightforward. And then if I'm asked, is this function continuous everywhere? X squared in itself is continuous everywhere. We know that, right? Because it's a polynomial function, there's no problem with the denominator or anything. We know this is continuous everywhere. However, it's important to consider that it's made of these 2 functions, f and g, right? And we know that g, both these functions are not continuous at x is equal to x is equal to 0, right? That's going to give me 1 over 0 for both of them. It's infinity, and that's a point of discontinuity for me. Therefore, when asked for this composite function, you can be as straightforward as x squared. However, it's important to understand that this function is not, even if it's x squared, it's not going to be continuous everywhere. It's not continuous at x is equal to 0, however, because it's made up of f of x and g of x, these two functions, right? And both of them are discontinuous at x approaching 0, right? So that's like something that you need to be wary of. All right, now we have this fun question which has to do with the intermediate value theorem. So what it means is that what the question is basically asking, is there a number that is one more than its cube? Simple question, the first thought that should pop into your head is that, hey, this is not even calculus. What is the concept that I'm going to use here? But then you think about the function that you can use to represent this problem. So you have f of x, which means that a number which is one more than its cube, right? So x is equal to x cubed plus 1. A number which is one more than its cubed. So this is the condition that needs to be satisfied. I can move this around to say x cubed minus x plus 1. Take the x from this side. Let's call this function f of x, right? Now, in order to satisfy this equation, this f of x has to be 0, right? Obviously, because if this has to be satisfied, I took the x to this side and I'll be left with a 0. So f of x has to be 0. And now I can use the intermediate value theorem, right? What I do is that I say, what is the value that so obviously I know that this is a cubic function, this is a polynomial function which is continuous everywhere. That I know, right? Now, what is the value that I get when I take x is equal to 2? Right, f of 2, that's 8 minus 2 plus 1. 6 plus 1 is 7. Straightforward. And what is the value that this function takes when x is equal to negative 2? Pretty simple. Negative 2 cubed is negative 8 minus negative 2 plus 1. Negative 8 plus 2 is negative 6. Negative 6 plus 1 is negative 5. So, f of 2 is 7, f of negative 2 is negative 5. And I can use the intermediate value theorem here to say that, hey, if this function is continuous everywhere, then it's also continuous between f of negative 2 and 2, right? This interval here, negative 2 to 2, it's also it's continuous in this interval. And I know that this, when I have f of negative 2, right, that is negative 5. And this is 7. And 0 lies between these two values. And for the condition to be satisfied, a number one more than its cube, the function f of x has to be 0. So I know that there is going to be a value between negative 2 and 2 for which f of x is equal to 0. So I can prove this using the intermediate value theorem, right? This is an interesting application-based question for intermediate value theorem and higher order thinking skill type question. Anyway, so that's all for continuity. Let's move on to the next topic, which is horizontal asymptotes, which is again pretty similar to something we covered in the first video, which was vertical asymptotes, right? So what we have here is that limit x approaching a of f of x is equal to infinity or negative infinity. So in that case, I'm just going to put plus and minus on top of each other. This is how you represent this. And this means that A is a horizontal, this means that A is the vertical asymptote. This is the condition for vertical. I'm just going to write VA for vertical asymptote. For horizontal asymptote, it's the opposite. I have x tending to infinity. This could also be negative infinity for f of x. And that's going to be value L, which means that L is the horizontal asymptote. So for the horizontal asymptote, x has to tend to infinity, and L, whatever value I get when x is approaching infinity for a function, L, right, any constant, that is going to be the horizontal asymptote. In case of vertical asymptote, it's a little different. I have x tending to a for f of x. Now I have to find this a, this constant a that x is going to approach, that is going to give me a value of positive or negative infinity for the function f of x. That's going to be my vertical asymptotes. So it's like pretty similar, they're both related to a large extent. Graph, if I look at the graph, right? Just looking at the graph, I know that this function, let's call this value -2, and this value as 1. So the vertical asymptote for this function, right, that's when this function gets parallel to the y-axis. And this function gets parallel to the y-axis at x is equal to -2, right? I can see that this line is going to go parallel to the y-axis. Hence the name vertical asymptote, right? So the vertical asymptote for this function that I drew, f of x, is going to be -2. The horizontal asymptote is when it's horizontally parallel, to the x-axis in this case, which is going to be at y is equal to 1. So y is equal to 1, this value is going to go to infinity. So what I'm saying is that when x is approaching infinity, right, the value that this function stays at is 1. That's my L, that's my horizontal asymptote. So that's where the terms came from. And there's this interesting theorem, which is actually pretty straightforward, that's often used to solve questions. This theorem is basically, it says that limit x tending to infinity, even negative infinity, both of them, for 1 over x to the r is equal to 0 whenever r is greater than 0. So r is 1, r is 2, I have 1 over x squared, x tending to infinity, that's going to be 0. 1 over x cubed, x approaching infinity, or negative infinity, 0. So this is like an important theorem that we use. So it's a result that we already have, and we can use this in our question. So let's go and look at a question real quick. So I have 3x minus x minus 2 over 5x squared, or 3x squared, my bad. 5x squared plus 4x plus 1. This is my f of x, right? Let's say I want to find the horizontal asymptote for this question, for this function. How do I do it? Pretty straightforward. I have limit x tending to infinity, 3x squared minus x minus 2 over 5x squared plus 4x plus 1. What I do next is, because I'm dealing with infinity, right? This is how you perceive. I write this as limit x tending to infinity. That stays the same. I divide my numerator and denominator with the x value of the highest order. So in this, the numerator or denominator, let's look at the numerator, right? What's the highest x that you have? It's x squared, right? Because it's a quadratic polynomial. So I divide the numerator by x squared. So I have 3x squared minus x minus 2 over x squared. And then I divide my denominator, looking at its highest order, which is x squared again, by x squared, right? So I have 5x squared plus 4x plus 1 over x squared. Now, if I'm dividing it, I have to multiply it by x squared, and this also by x squared, but those cancel out, obviously. So it works well in this case. I can write this, I can simplify this as limit x tending to infinity. 3x squared over x squared is just going to be 3, minus 1 over x, minus 2 over x squared. That's my numerator. My denominator is similar, 5 plus 4 over x plus 1 over x squared. And when x is going to go to infinity, right, this is going to go to 0, this is going to go to 0, this is going to go to 0, and this is going to go to 0. So what am I going to be left with? I can use limit laws to simplify this further, but I know that this is going to be 3 over 5. So 3 over 5 is my horizontal asymptote, right? And that's the leading coefficient for the numerator and denominator, 3 over 5. Pretty straightforward there, right? Okay, let's look at another question. Let's say I have this function, root x squared plus 1 minus x, right? Again, if I'm asked about the horizontal asymptote, I have to find the limit when x is approaching infinity. And if I just plug in infinity, I'm going to get infinity, root infinity minus infinity, which doesn't make sense, right? I can't evaluate infinity plus infinity or infinity minus infinity, especially infinity minus infinity. It's just weird, right? What do? I proceed in this way. Limit x tending to infinity. I write the function out, x squared plus 1 minus x. Limit x tending to infinity. I can rationalize it now. Previously, we were rationalizing because we had a 0 over 0 form, right? And then cancel the numerator and denominator out. Some things used to cancel out and we would get a constant value. But in this case, I'm rationalizing because I have infinity minus infinity in the numerator. What happens when I rationalize it? I have x squared plus 1 minus x. And then rationalizing it, you have a minus b, you multiply it by a plus b. So that's going to be root x squared plus 1 plus x over root x squared plus 1 plus x. So what do I get when I simplify this? I get limit x tending to infinity. So a minus b times a plus b is a squared minus b squared. This is my a, which is x squared plus 1. And my b is x, right? Minus b squared, x squared. Denominator just has root x squared plus 1 plus x, right? That's what the new denominator has. This gets cancelled out, and I'm left with 1 over this denominator. Now I can just plug, I know that, when I plug in infinity in the denominator, I don't have any x term in the numerator. But in the denominator, if I plug in infinity, I'm going to get root infinity squared plus 1, that's just root infinity, plus infinity. And infinity plus infinity, we know that's infinity. So it's going to be 1 over infinity, which is just 0. So this is what the horizontal asymptote for this function. This is what it this function is going to, this limit is going to look like. Pretty interesting that we use rationalization in a different manner in this question. Okay, now let's discuss another interesting question. So I have this function f of x, which is root 2x squared plus 1 divided by 3x minus 5. And if I'm asked to find the horizontal and vertical asymptotes for this function, how do I proceed? Let's find the horizontal asymptote first, right? Simple. I start with the limit x tending to infinity. That's how you find the horizontal asymptote for this function, which is root 2x squared plus 1 over 3x minus 5. We proceed in a similar fashion. We divide the numerator and denominator by x. Why do we do that in this case, right? Because in the previous question, what we did was that we looked at the highest power of the numerator, highest power of the denominator, and we divided by that. So denominator makes sense. It's just x, right? The highest power of x. So we divide that by x, right? That we understand. And times x, sure. But the numerator, the highest power, it's not x squared. There is a square root sign on top of that. So root of x squared is x, which means that you're going to divide the denominator by x. And let's see how that works out for us. So I have root 2x squared plus 1 divided by x times x. So these two get cancelled out, right? What am I left with? Limit x tending to infinity. And okay, let's look at the numerator once, right? So I have x here, and x is going to approach infinity, so x is positive, right? So what do? I take the x inside the root sign. And for that, I add this squared here, right? Because if I take that outside of the root sign, I'm going to get x as I had before. But to send it in, I have to raise its power to 2, right? And the denominator is just straightforward. That's just 3 minus 5 over x. Now, I can simplify the numerator further. I'm just going to go into this right now. It's not super mandatory. And then 3 minus 5 over x. And then, when x is going to approach infinity, this is going to be 0. This is going to be 0. I'm going to be left with root 2 over 3. So that's one of my horizontal asymptotes. Now, I said one of my horizontal asymptotes. Why did I say that? It's pretty important why. Because your horizontal asymptote can, work on the negative infinity side as well, right? Therefore, it's important to consider x tending to negative infinity too. So let's see what we get if we do that. So x is approaching negative infinity. I use the same function. I have this same thing, right? I divide it by x. This is a step where things get interesting, and negative infinity. When I send in the x inside of x squared, this time I introduce an x, right? I divide the numerator and denominator by x. I introduced a random quantity x. However, it's really important to consider where x is at this moment. X is approaching negative infinity, which means that x is a negative value. Therefore, when I send it in the bracket in the root sign, I have to include a negative sign. The reason why we do that is because, right, so this is 2x squared plus 1 over x squared, root, right? Why we do this is because when x is going to go to infinity, right, negative infinity, this value, when I take the x outside this time, it's going to give me negative, right? Because when x is negative, what's root of x squared? That's negative s, right? So 25, if I find the square root of that, that could be 5 or negative 5, depending on where my x is, you know, 5 in this case, or like negative 5, whatever, it's one of these, right? In the previous example, it was positive, that's why we consider 5, right? I'm just giving an analogy here. But this time x is approaching negative infinity, which means it's a negative value, so if I find the square root, I need to take into account the negative sign. So what happens then is that I get negative, I take the negative sign outside, x tending to negative infinity, and I proceed the same way. I'm going to be left with root 2 over 3, which is just negative root 2 over 3. Which means this is really important here, because when you're finding the horizontal asymptote, you have to take into account the positive infinity and the negative infinity. And when you're like putting the x inside a root sign or something, you need to take account of the negative sign, because x is approaching a negative infinity, which means that x is going to be negative. Therefore, there are two horizontal asymptotes to this function, root 2 over 3 and negative root 2 over 3. Now we can just look at the vertical asymptote, but that's not too much work. Why? Because we just look at the function and we see where is this function going to go to, for what value of x is this function going to infinity? Simple, right? X, when the denominator is going to be 0, right? That's when the function is going to go to infinity. For the denominator to be 0, I have 3x minus 5 is equal to 0, x is equal to 5 over 3. Straightforward, you know, right? The vertical asymptote is 5 over 3, and the horizontal asymptotes are root 2 over 3 and negative root 2 over 3. These are my two vertical asymptotes. Now, you know what? Let's go over one more problem, and then let's call it a day. I have this function, f of x, which is e to the 1 over x. And let's say I want to evaluate limit x tending to 0 minus 1 over x. How do I do that? Simple, right? Limit h tending to 0, e to the 1 over 0 minus h, which is just limit h tending to 0, e to the 1 over minus h, which is limit h tending to 0, reciprocal, right? I get 1 over 1, e to the 1 over h. When it goes to 0, I know this is going to be e to the 1 over 0. E to the 1 over 0 is e to the infinity, which is just infinity. This denominator is going to be infinity. 1 over infinity, that's 0. So this is the limit. This is how you evaluate the limit. This is a pretty straightforward thing that we have covered before, right? In the question where we had 1 over 1 plus e to the 1 over x. We already covered that there. And actually, let's go over one more example real quick. And let's say if my function is sine x, and I want to find this limit. Limit x tending to infinity for sine of x. We cannot find this limit, right? Why? Because we know that the sine function, it's an oscillating function that goes from, you know, sine of 0 is 0, then it goes to 1, then goes to 0, then back to negative 1, then goes to 0, 1, negative 1. It oscillates between 1 and negative 1, right? When you vary the angle, you increase it by pi over 2 or 90 degrees, it's going to go to 1, then it's going to go to 0, then negative 1, then 0. It's an oscillating function. So when x is going to approach infinity, you don't know what multiple, you know, what this x is, right? If it's like n times pi, where n is odd, then you know that this value is going to be like 0, right? And so like there's no way of telling what this limit is going to be, right? Because it's an oscillating function. You cannot make any claim about this. Therefore, the answer to this function is this: cannot be evaluated. Or in other words, limit does not exist, DNE. This is another short form or an acronym that we use. So this is like what we're gonna cover in this particular video. We're gonna go over another concept of horizontal asymptote where we link horizontal asymptote with precise definition of limit, which we have covered in the past. And we have like one or two more examples after this, and then we're gonna go into my favorite part personally, which is rates of change or differentiation, and try to see how limits, what we've been studying so far, relates to differentiation or rates of change. So that's all for this video, and I'll see you in the next one. Stay tuned.